What's up, YouTube? So a few weeks ago, one of the channels I love the most, called PBS Spacetime, posted a video on a nuclear physics challenge, and I decided to take it a shot. It was basically calculating the possibility of an alpha particle teleporting out of the nucleus in a polonium-212 atom. I'm gonna link the video in the description, but here's a clip.
There are no stable isotopes of polonium, but one of the least stable is polonium-212. It has a half-life of 0.3 microseconds, meaning half of any sample of polonium-212 will have decayed to lead in that time. That's also the half-life of an individual nucleus, so after 0.3 microseconds, there's a 50% chance that a given polonium-212 nucleus will have decayed. The challenge for today is for you to figure out the tunneling probability for an alpha particle to escape from a polonium-212 nucleus. Okay, here's some useful info. Picture an alpha particle as being trapped inside a box. The walls of the box result from the strong nuclear force, which holds the nucleus together. However, that force has a very, very short range. The particle is bouncing between these force walls, and every time it approaches one wall, there's a chance it'll tunnel through. You need to find the tunneling probability for each one of these encounters with the wall, a probability that will add up to 50% over the many, many encounters that happen in the 0.3 microsecond half-life. A good first step might be to figure out how many times the alpha particle encounters the wall in that 0.3 microseconds. Some stuff you'll need. To get the number of wall bounces in 0.3 microseconds, you need the size of the polonium-212 nucleus, which you can calculate from the nuclear radius relationship, which relates the radius of a nucleus to the atomic mass number. I'll let you Google that one. You'll also need the velocity of the alpha particle. The alpha particle ejected in the decay of polonium-212 has a kinetic energy of 8.78 MeV, and you can calculate the velocity using the equation for kinetic energy and the mass of the alpha particle. Again, Google away, my friends. This info, plus drawing some of your own diagrams, plus some basic algebra, is enough to get you the probability that an alpha particle will tunnel out of the polonium-212 nucleus on any one encounter with the edge of that nucleus.
So, as this guy says, the atom polonium-212 has a half-life of 0.3 microseconds. Nothing to do with Half-Life 3 or anything. But the possibility of an alpha particle teleporting out of the nucleus was a bit of a tough calculation, but here I'm going to show you my calculations. Now, first off, you put the data to start as polonium-212, the half-life and everything, and you put on one side all of the powers of 10 that the International System of Units requires, and as this guy says, you need the nuclear radius relationship. You got it here, and you know that it's 5.963 femtometers. He gives you the amount of energy that you can convert to joules, 1.406 picojoules. The mass of an alpha particle, I know that Chinese character looks a bit weird, but bear with me here. You know that it's 6.644 times 10 to the minus 27 kilograms, and you just do the conversion to get the powers of 10. In this case we need 2 because it's minus 24 minus 3, 2, which gives us minus 27. Then, after that, I decided to use a glass surface, my bathroom mirror in this case, and you get the equation for kinetic energy in the top, and a bunch of calculations that lead you to an x squared for the velocity of the particle, and square rooting it through the method you see over here gives 20 million meters per second. Knowing that speed, you have to know how much time it takes for the particle to bounce between one part and another of the nucleus of the atom. In this case, it was 289 yoctoseconds. Now, I made a huge mistake here. I mistakenly used rule of 3 for divisions, while I shouldn't have used potentiation the way that it should have been, as PBS saves time showed in a paper that I'm showing over here. The answer was, in this case, 48 times higher than it should be. You know that it's 45.1 when it should have been 1.74 times 10 to the minus 15%. But at least I gave it a try. I got the answer wrong, hilariously wrong, but I did it. There you go. That was my take on the nuclear physics challenge. I don't know if you can try it, if you want to try it, if you're brave enough to try it, go on. There is no time for the offer that this guy did, but you know, you can try it. You can try it for yourself if you want. You should get that result. Math is really fun. And until next time, stay tuned, stay cool.